So let's get started. So I'm going to do my talk in the IDE. I think it's nice to be close to the code, keep it real, keep it with real Scala code, real type systems there always present. So cast your mind back to high school maths. That's where I first learned about the function, the concept of a function, and what it meant when I first encountered it at school was that it was something that went from double to double, and it had various implementations. And hopefully you recall studying the domain, which is basically the acceptable inputs to a function, and the range, something's called the codomain, which are possible outputs of a function. And maybe you remember some functions like the square root function, just for revision, there it is. The reciprocal function, there it is, plotted, and the probability complement function, basically to find probability P, the probability of not P happening, there it is. So we can define those three functions as having the type double to double, as we can see on the screen here, mapping a double onto double, and that kind of works, but it's not really good enough, is it? Because we can very quickly start creating values that type check using that double to double function type, but are in fact silly. We can try and take the square root of -1. We can try to take the reciprocal of 0, and we can try and compute probability complement of something that simply isn't a probability. Now, just while we're here, I'll just point out a little bit of syntax. If you need to write identifiers in Java, in Scala, that have funny characters in them, you can do so, and the back quote is your friend, your way of getting basically any acceptable character into your identifier. So it's not good style, but if for some reason you need to do it, then you've got that option there. So I hope you can see that the type signature double to double is a bit of a white lie, and can we do better than that? So a total function is defined over its whole domain, while a partial function is defined over a subset of the domain. So I've given you three examples of partial functions. That is, there's at least some part of their domain. In the reciprocal case, it's the smallest part, it's the infinitely small part at 0, where the function is not defined. So when we're programming with any old function now, regular programming from some function from an A to a B, if we want to see that as a total function, which by default is kind of implied that it is, then we're stating that every value of type A is acceptable input, and we're stating that we should only ever get B back. So people, users of static typing, like to think that generally in the sphere of programming, we're the careful, responsible ones, and that's probably true at that end. But nonetheless, we certainly flout this principle of programming programming with functions that are total in their types all the time. And here's just a piece of code that I've created that's representative of plenty of code I've seen in business systems. It's a method that looks up tasks, that takes the job code, and you find attached to it some documentation that explains the format of the job code. The job code consists of a business unit ID, which is 3 letters, followed by the charge code that task is going to be charged to, followed by the task number, and there it is. And you can see that that's a pretty structured piece of information. But we've given this method, this function, find task, the type stringed task in this case. So if that was a total function, we'd be stating that it's defined for all string values. Whereas in fact, in the universe of possible string values, the set of strings that actually are the valid job code is some tiny, infinitesimally small fraction of them. So of course, we can give it stuff that will type check, but is in fact rubbish. And really what I've just shown you is the central message of my talk tonight. It's just being aware of this issue and striving to move towards programming with total functions, which is of course a sort of a impossible goal to reach in entirety, but at least you can kind of know where you're going, where the goal is. That's a step along the way. So being aware of it. So what's an action that we can do that will get us towards our functions being less partial? To do so, we need to invent precise types that describe our data. And when we get unknown data, we have to first validate it to lift it into a more precisely typed data, and then we can use it with functions that are defined over those more precise types. And this gets to something that you see a lot, which is that people think that if they're doing static typing, they're evidently using some kind of type to describe their data, like a string or an int or something. The fact that you're using a type doesn't necessarily mean you're using static typing particularly well. So, you know, it's not just like, oh, I'm doing static typing. Oh, good, I'm in compliance. I'm getting rid of my bugs. I'm programming safely. Actually, it's much more of a spectrum, and maybe the real spectrum, I think, to measure yourself on is how much of my domain does my type, how accurately does my type describe my domain, and similarly with my range of my functions is what you should measure yourself on, where perfection is the type that describes the inputs to my functions. Every value that can be of that type is a valid input, and my function cannot emit anything outside the range, and the range kind of tightly bounds the values that can come back. If that makes sense. So it's about using static typing like you really believe in it. So I want to sort of use probability as a kind of case study to explore to what extent this is possible, and you run into problems. It's not it's far from perfect. So probability is essentially, we can model it as a floating point number, but it's always in the range 0 to 1. That's the extra constraint that we're going to model for a type. Now, as of Scala 2.10, there is a really nice a new feature known as value classes that lets us work with precisely typed numeric-like values, primitive-like values of this type much more efficiently than in the past. And essentially a value class, of which this is an example, looks like a normal class, but it extends any val. And any val is like generally the primitive designator that previously you hadn't been able to extend yourself. And so here we're defining a probability that holds a value of double, here value, and extends any val. And basically what the compiler is going to do is actually de-sugar this down to being just a raw double. So there's not going to be a class, there's not going to be an object allocation when you create one of these guys. The compiler is going to actually be passing around a double, and but it's going to give us A, the methods that we define, but B, it's not going to give us all the basic methods of double, and it's going to be held in a separate compartment to normal doubles. It won't be assignable to normal doubles, and then doubles won't be assignable onto separate types. Constructor for a value type has to be primitive? Yes, it does. So, so before we move on, a note on this. I put some protection on this constructor. So this protected keyword applies over the constructor. And the reason I want to do that is I want there to be a clearly defined way that you can get to this type. I don't want anyone to be able to just create these things. I'll show why in a moment. But let's have a look at some wins. So having defined a probability type, the multiplication operation over two probabilities is inherently safe because two intervals in the range 0 to 1, when multiplied together, must always fall into that range themselves. So that one we can do. However, in the case of addition, subtraction, and division, we haven't really got a win here. We can revalidate our operation, but these can still fail at runtime. However, the OR operation, which on another value which is independent can be done and statically guaranteed state. So just defining a narrow type law probability doesn't make all the problems go away. It sort of certifies the value is in a narrow range, but you're still going to have the problem that operations over a narrow type may leak out into a wider type. So I just want to look at like how you can actually construct probabilities from looser types. I've created range. So range comes from the Guava library. Basically defines an interval. I think intervals are tremendously useful types that really should be in the core, and they're just under-recognized in programming languages. Just intervals are just, I use them all the time. It's great that it's in Guava, but I think every new standard library should include a numeric interval type. Myself. So let's look at two ways to go from double to probability. No. Oh, sorry. It's got a thing called a range, but it doesn't define a numeric interval. Yeah, it defines like a sort of sequence of numbers, but not like a range can be open or closed at either end, and it can be a range of integers or doubles. Scala's range is more like a generator. So, firstly, this as is kind of like a cast. It just takes a double and goes to probability. So naturally, there has to be some kind of handling of the failure case, because not every double is a probability. So we're lifting from a wide type to a narrow type here. So otherwise we're just going to blow up if we don't. So I think as a designer, that's fine for a small script. If it's just a couple of lines, or you don't really have any strategy to handle the failure case, then just fail fast and let your fail go global. But I think if you're going to take an exception, that's kind of like saying terminate the program. You know, this idea that you kind of throw an exception and expect to handle at a higher level. I'm really moving away from that. I think if you want to model the failure case, it should show up in the type signature, not as an implied exception. So the other way to do it is to use a validation. And a validation is basically like an either type. It's a this or a that, but it's an either type where there's a definitely defined role for each side. And let's have a look at it. So a validation holds a failure type and a success type. So it's a right, they call it a right bias either. And the reason they say it's right bias is because if you map over a validation, you're basically mapping over the success case. Whereas if you map over an either, it sort of says, well, which side did you want me to map over? There's an ambiguity there. So we're using validation comes from the Scala Z library, and it's pretty simple. The probability range contains our value, then we lift it into this probability, and return that, and the success is a piece of Scala Z syntax sugar that lifts our probability into a validation of probability, else we just fail with the original value, and that lifts it into a validation of double. Another kind of little design choice I'm coming to favour with validation is actually returning the original type, so double rather than string, as the failure case, because if you render everything to a string, it's human readable, but it's not machine readable. That's the failure side. So there's no chance for a computer to sort of understand what the value was that failed. Whereas if you leave it in the original type, you haven't thrown away any information by doing so. So I kind of see it like if you're trying to go from a wider domain to a narrow domain, you sort of fire your value at the validation, and if it lands in the acceptable bin, then you get back a validation containing the narrower type. Otherwise, if it lands outside, you get back the original type, because you kind of miss the narrow target you're aiming at. So
what's your reason for failure? So like, if it was because it was 0 and it was -1, or there might be another different reason for failure. So with a string, obviously we've got the string negative thing, it could be a number of different failure options. So by returning an original number, we have lost sort of contextual reasoning for the player.
Yeah, you could argue that. So certainly there might be cases where you want to describe what the rule was, but the more I thought about it, I started to think, well, have you really lost it in this case? If I try and validate something to probability and I get back a double, I kind of know. Like, I'll know from that why. I look at it and I'll see that it's either less than 0 or more, and I could fairly trivially then turn that into a string message. I could say value blah is not in this range or something. Potentially, that was my thinking.
There's no reason why you couldn't just combine have both best of both worlds, have the double and a string, or and or whatever you like.
If it was a compiler, for example, you just said, here's your code back, rather than saying, there's actually just a semicolon on line 34, then, that would be one extreme. The fact you return the input, the code, but the user's going, well, thanks for that, but why did it fail?
Yeah. This works well in small cases, but actually later on, you'll see a case where when I start to compose bigger validations, I move away from this, and move towards using strings. There's some good reasons for that. So the way I like to think of this is that the validation step is kind of forming a barrier or a membrane around this richly typed domain model, where you start to use types to kind of certify some additional properties about your data that you want to work with. And when we go from the weakly typed world outside into the domain, we've got to get through our checks, our validation checks. But once we've got inside, we can kind of count on the invariants that our richer type system has. So I've drawn a kind of diagram of this. It's very much, I've kind of based it on the whole metaphor of a cell. Kind of you want to work in a richly typed domain model, and the validation kind of sits at the boundary and allows things that fit in the richly typed world through, but anything that's poorly typed just keeps back. So that's the general gist of it. And I think for a tiny little application like a little script, you don't gain a lot from it. But as your application gets bigger, and as you do progressively more complex stuff in here, your payoffs get bigger and bigger for the extra work. So in a way, this is kind of defensive programming, but it's really different to the sort of trust no one style that I've sometimes seen. I've worked on plenty of big enterprise systems where every single module opens up its inputs and does all the checks on them, because no one really trusts each other. And such a succession of different companies and contractors have worked over the system that any kind of strong invariance has been lost. And it seems to me that the best way to try to get away from that situation is that you've got to really sample with a precise type. And then it doesn't matter who works on the code after you. If that type's maintained, and the only way to get to that type is to go through a validation, then you're still going to retain some kind of strong guarantees about what's working. So it's kind of it's a soft center. People in security sometimes call this about the crunchy hard boundary in the soft center, but you're using the type system to kind of give you laws that show you that your center can be soft and gooey and have a lot less validation and defensive logic in there by certifying that you must have passed validation to get it. We're pushing the trust checks out to the boundary. Okay. So what about if we want to do like maths over our probabilities? Like we might have a bunch of probabilities we want to sum over them. So let's have a look at the code you can do that. So Java gives you this whole bunch of type classes for representing numbers. The top one's called numeric, and for numbers that are fractional, i.e. not whole integers, there's a subtype called fractional. And this is what you have to do to be a number in Scala design. You have to define this big type class with 1, 2, 3, 4, 5, 6, 10 different methods on it. And that's because that's the current type class design in Scala is very, very big, sort of coarse-grained type class that throws in all numeric functionality into something that can't be broken down. Now, I've been on actually a crusade to change this. I've submitted a patch to Scala which breaks this down into fine-grained type classes, separating out multiplicative, additive, subtractive subtraits. And this gives an example of why that was worth doing. Like, for probability, plus makes sense, minus makes sense, times makes sense, divide makes sense, to double and to float makes sense. But these four, you're forced to define them to be a number, even though really they make no sense. How are we going to negate a probability? It's not even in the definition of probability. From is, well, for something that lies in the range between two integers, that doesn't make a lot of sense, and so on and so forth. So far, I've got absolutely no traction with getting anyone to care about this issue, but I'm going to keep beating on about it to those people, captive audiences who have to listen to this, to try to spread the word on why this actually matters.
You're not alone there. Like we discussed before, that's basically a copy of Haskell's class system, and there's a long running argument in Haskell for the same problem. So you're not on your own, except you're living in Scala.
Good. I feel better. All right. So now let's talk about kind of good types and bad types. Like, we've got this idea that we're going to start to grab everything, all of our types, and try to make them fit. Where does that start to run out? Where do we get to the point where we just go, no, these microtypes, these super subtypes are just really silly? So, what about a dice? So, what if we wanted to have a type for the value of integers between the value of 1 and 6, or maybe we're designing a board game or something. So, we can kind of do that. There it is, nat6 takes an int, and we can create a little validation there that will validate into it. But where this kind of goes wrong, I'm not saying this is terrible, but it's of limited usefulness. It's basically because all the stuff that we want to do with this value that's 1 to 6, if we just add two values that are 1 to 6, we get a value that isn't necessarily in the range 1 to 6. So we've gone from this precise type, and the moment we do anything with it, we drop back to the broader type. And similarly, it turns out that for all these cases, not one of them will actually result in a type of nat6. So they'll all have to result in something broader, like integer. So most operations that we can define over it sort of pop out of the narrow type. So in algebra, I think that the correct term is to say that the nat6 is not closed under most useful operations. And ideally, types are actually closed under useful operations. Another way of saying that is that they have endo functions, or functions that map from themselves onto themselves. And if you think about a string, you can reverse a string, you can slice a string down to a substring, you can splice strings together, and you still end up with strings. So you can, once you get into the string type, you can kind of do a lot of useful stuff and still stay in that same type. Whereas once you get into this type representing a dice roll, you can do hardly anything without popping out. So that's kind of the difference. This is my little diagram. If we're going to have precise types, and we lift from a broad type like integer into a precise type, if everything you do just pops out again, then it may have been of some value. It's still certified that it was in that range. But in the string case, there's lots of operations that take us back to another string. And even the ones that don't take us to other richer types, like we can go to char, or we can go to int with an index of operation. So it can take us to places we want to go. Whereas in this case, we're all dressed up, but we've got nowhere to go.
Scala.
Plus, minus, and good for showing the modules to wrap it out. So it's plus 1.
Right. True. And that would be an algebraic proof. Yeah, I was thinking of a dice roll. I was thinking of trying to model a board game where we might roll 3 dice and have to add them up, and we're going to get some result. But yeah, in some cases, then it does make sense.
But I mean, in a way, it's a strawman argument because there's this type of string which has infinitely many things in it, and there's this type of 6 things, and like, well, the thing with infinitely many things in it has always one kind of functions that go back on the space of infinitely many things. I mean, I'm not surprised that there's a type of 6 thing that doesn't have that many interesting operations because it's a boring type. So, you know, I kind of think, yeah, of course.
Okay. Main point I'm trying to make is that I guess earlier I was arguing that we're too lax with our types. We write functions that admit lots of things that aren't valid inputs. So, like, if that leads you kind of down this path, where does it get silly? Like, this is kind of the counterforce. I don't know. In design, often the right answer is the sort of grey area in the middle, but this is the sort of counterforce that if you get too precise, you get to these silly types that aren't that good.
There are sort of extremes. You've got infinite one and very tight range of the other. The end of the useful life of the type of the bond type is somewhere new.
Yeah, but I think particularly that property of closure, if you've got operations from the type to itself, can make the type a lot more useful. Like in the probability example, there's not a lot of things you can do with a probability that retain a probability, but multiplication one, and that's fairly useful.
The Scala questions stuff, but interesting on like a map operation on something might get you back like a list. Map might get you back a list, but it might get you back to something else, depending on what you're actually doing inside the function. So that sort of takes it another way. It has can build from, it has those 6 things. So it's sort of another different take on that same sort of problem. You might get back to start with, but you might get back to something more general type of same situation.
Yes, yeah. That's a really interesting area. I'm not going to talk about that tonight, but that whole design is probably worthy of a talk in itself. So it turns out that that's goes under the name functional dependencies in the Haskell world, and it's kind of like when it was invented in Scala, no one recognized its lineage from the Haskell world, but that's now becoming better understood. And there's a guy, Miles Statham, who's got a quite interesting blog post on that. And yeah, that can build from design is actually not as novel as it might seem to Scala people. There's quite a few precursors in Haskell, but it's enormously powerful and enables these extremely polymorphic behaviours that go far beyond what you can do with object-oriented polymorphism. I'm a big fan. So there's a trade-off here. Alright.
So Ben, are you saying you wouldn't encode the 6-sided dice that way? I'm not sure what your argument is. You're saying you wouldn't do it that way because the bombs you've identified
I don't. It depends how important it is for your particular problem domain. But I'm just saying, think twice before you go narrowing the types too far. It's probably, my argument is no more specific than that. I'm going to say that this is a design talk rather than a really precise crisp theory talk. So I'm just kind of talk about design forces and not commit to any particular position. Yeah. Okay. So next topic, I want to talk about types that describe aggregate properties. So let's look at an example of probability distribution. So the probability distribution is basically to have a probability distribution, you first have to have this concept of an event space, which is all possible happenings in some domain. And a probability distribution is the assignment of a set of probabilities to all the possible things that could happen, so that they sum to 1. So probability distribution is kind of this collection of some finite or infinite collection of probabilities that have the constraint that together they collectively sum to 1. That's kind of a rough modelling of that. So yeah, the main point is that they have a constraint across an aggregate collection of values. It's not a property of each individual value. When we have a list of int, we're not really saying anything about the relationship between the different members of the list. We're just saying that individually they're an int. This is a different concept. Here the type speaks about something about the nature of the collection as a whole. In this case, that they sum to 1. But I think these are quite useful for other reasons. Like, for example, the ordering of elements is another. Orderedness is another relationship that is not a property of individual elements, but a relative property. The sorted set and sorted map. And I thought a little bit about this one, and it struck me that that's not, knowing that they're ordered alone is really not terribly useful. You need to know at least 2 more things for any ordering to really get much value at it. You need to know what ordering are they ordered by. Otherwise, from the outside, that type is next to useless if you don't know the ordering. But secondly, you need to, for any ordering, it's going to impose 2 possible kind of orderings, ascending and descending order. If you don't know which one it is, then again, you don't have much useful information. So, what? I would say that for any ordering, there are 2 directions that arise. If you think about writing a type signature of a function that's going to consume some ordered group of elements and it's going to rely on their ordering property, I guess what I mean is that you need to specify somehow in the type signature the type of ordering that they're ordered under and the direction in which they're coming to you. Because if they come to you from A to Z, it's obviously completely different to if they come to you from A. The type of the ordering that is each direction. Right. So they just come in pairs. Yeah, that's different. Distinctness of elements. So we already have a set, and a set really says something about distinctness. And distinctness is definitely a group property, not an individual property, because individually something is not distinct. And then the norm of the elements. So here's an example from an earlier talk where I was showing that we take for some vector type, which is just like a pair of numeric values, we can define this direction method on it that returns you a vector with unit length. And in this case, this with unit length is actually attaching an additional piece, an additional certification or guarantee to the output type, which is saying this has a Euclidean norm of 1, i.e. when you sum these together, so sum the squares and take the square root, it'll come to 1. That was going to take that out. That's not terribly interesting. So let's take that out right now. I decided that was. So something to think about. Can anyone think of any other types where we describe aggregate qualities? That was all the ones I could think of. But anyone anything jumps out. The collection types where something about the collection type also describes something that's a relative or aggregate quality. Maybe something to suggest at the end if you can think of it. So just going back to the original 3 functions.
So I guess you use some of your invoices, customer
a time where a static type is associated with some object of container, and the type describes something about the relative nature of the things that are contained. Like, for example, a vector is a container of numbers, but the unit length type describes some relationship between those numbers, in a set, it's a traversable of some content type. But the fact that it's a set describes well, in part, one of the things that it gives you is the three elements of the thing. The Scala set. And in this case, it implies that the elements are ordered according to some ordering. It's a type that a container or collection has that describes some aggregate property of the elements that live in it. It's something I'm just interested in at the moment.
Yeah, I think it's just elaborations of nature. And statistics is by nature of the, it's a collection. And so average, mean, standard deviation.
Right. Yeah. Are there times when we actually put that into a type system? Yeah. Because obviously I think you could have something that's the average of 0. Its mean is 0 might be useful type. It could be distributed anyway, but the fact that it's centrally applied to 0 could be a useful property.
You can define any predicate you want. Does not contain the value 12.
Sure. No, I was more meaning, can you think of examples from while? Like from APIs you've worked with or from the standard libraries that where stuff out there?
Positive, non-negative numbers.
Right. Yeah, true.
I was being slightly facetious with my point about propositions, but not entirely. I think you could kind of invent any proposition on natural numbers that would be ultimately even, odd.
But is that really an example, or is that more a case of the individual elements or even? But it's rather than something about the relative or collective. I guess a red-black tree implies that it's a tree that's balanced, or at least that there's a limited amount of deviation from balance. So, yeah, balance. Let's find balance. I couldn't think of that many examples where aggregate qualities of a collection are actually certified in the type.
Maybe a prime collection might be useful for creating hashes or something.
But again, how is that not just, like, if I had a type prime, I could just have traversable of prime. And it's nothing more, there's no whole greater than the parts. Like, if they're all individually prime, they're still going to be prime.
Instead of a double, this describes a set that actually is useful for hashing. Primes, look at the hash argument, that's like primes versus other collections of numbers which might not be set.
Right. Right. Like, you could say a positive. They call it like positive definite matrices or positive semi-definite matrices.
Invertible.
Yeah, invertible. That's what I'm saying. Yeah, invertible matrix. It's not a property of the individual numbers, but a collective. Okay. Anyway, let's move on. So just having a look at some of the other cases. So, what if we wanted to? So let's return to our first example, the square root function. If we wanted to write a total function that considers square root, then we have to ensure that we have a type to describe the acceptable inputs, which are non-negative values. So that's this guy that's on the screen now, the non-negative type. And we can define a nice safe square root that will always give you back another non-negative value. We can also define a plus value that will always give you a non-negative. We run into troubles with the other ones. They're going to pop out to double. We can't guarantee that. Well, we could do multiplication of two non-negative numbers, but we couldn't do, and actually for that matter, division, but only subtraction. So again, yeah, but in general, if we want to do any subtractive operation between two arbitrary non-negative numbers, which after all the type doesn't give us any information beyond the general category, So we have to allow the type signature to pop out. That's the trick with types of rules. It's got to be any two arbitrary values, or you could do the opposite situation. Yep, that's another one. So here we've got we use the same validation technique to represent something that is either non-negative or double in the negative case, and so on. But now I just want to look at the case of this find task. So imagine if you remember the find task, let's just go back to it and have a look at how it works. So the find task method takes a job code, where a job code consists of a business unit ID, then a charge code, and then a task number. So what if we tried to write like a more total version of the find task function that really wasn't going to fail us, or at least have a greatly reduced probability of failure? The way we might do that is write a find task method that took a business unit, a charge code, and a task number. And then we'd need three validation methods, which took a string and lifted that into a business unit, and a code and lifted that into a charge code, and lifted that into a name. And then we'd have a whole lot more type safety over this. And again, we're still going to have to do this work, but we're going to be doing it out at the boundary of our domain model. But as our domain model starts to get big, we're going to start to just think in terms of charge codes or business units and be passing them around. And we won't bother dropping down to strings. We'll always have those rich types available, or at least that's the hope. And we now have a whole lot safer ones. So how can you get from these guys three validations to a task? And this is where we can use this thing called the applicative builder in Scala Z. And this is actually like an extraordinarily convenient piece of code. It took me a while to get my head around it, but I'm going to try and convey it to you. So this takes the raw unvalidated types, the string for the business unit, the code, and the integer task number. It then runs them through their individual validations. Validate business unit, validate charge code, and validate that. And it glues these three individual validations together using this applicative builder operator. Now what this basically does is then says, alright, you give me a function that if they all validated all right, if I had a business unit of the type, a code of the type, and a number of the nat type, I could then, what should I do with them? And you just say, this is what you should do with them. You should go and find task. Now use the rich type. And the type of the overall thing, the result we get back, is either a task, which is our final thing we're seeking to do, or it's a string. Sorry, no, it's not. Validation NEL stands for validation non-empty list. We'll either get back a list of at least one string, which is our failure reason, or we'll get back our task. And if you think about it, there's an awful lot of boilerplate in that operation that we didn't have to write. We just wrote the bit that matters. How to validate our three inputs, and what to do with them if they were all valid. Everything else is factored away into Scala Z. So it's an awful lot of boilerplate hidden away from here. In this case, I had to use string for these, and I could have tried to validate this as an int. The reason I had to use a string is because we're now collecting together lots of validations together. So we need some way to sort of concatenate multiple validations on the failure side. And obviously a list of strings is a nice simple way to do that. Okay. Finally, the third case I wanted to show you was the reciprocal function. So we could have a non-zero trait and a validate non-zero, and a reciprocal method that now defines in terms of a non-zero value and returns a non-zero value. But is it really worth validating that a double is anything but zero and having a type to represent that? And when I first started this talk, I thought, oh, I'll just remove this example. I don't want to show examples that kind of run counter to my arguments. But then I thought to myself, well, actually, I'll leave it in because it's not like it's a really clear-cut case. You've still got to exercise your judgment. There'll still be times when you think that this type is not worth its weight. It's and this might be a case where you just say there's just not enough useful stuff that I can do with a non-zero value. Or maybe that you don't. Probably depends on the problem. So that's it. Any questions?